I'm delighted to introduce Madeleine Zurowski. She comes to us from Australia, where she was born and where she got 3 degrees from the University of Melbourne. But if you think that she's um, only an Aussie, while getting those degrees, she also studied at Berkeley and Princeton, and now she's doing a postdoctoral fellowship at the University of Toronto and also working in the Snow Lab in Sudbury, Canada. She's mostly an experimentalist where she's looking for experimental evidence of this dark matter, but she also works with theorists, figuring out how to do those experiments and what to look for and what the evidence means. And I don't know how you search for the dark. I'm really looking forward to this talk today and her explanation. Thank you so much, Madeleine.
All right. Thanks very much for having me today. That was a lovely introduction. As Daphne said, I'm a postdoctoral fellow in the Department of Physics here at the University of Toronto. What some of you might have picked up on at lunch is I actually am technically a Canadian. Both my parents are Canadian. So it was really nice to get the call up to move back to Toronto in a way. Just before I get started, I'm interested to know how many people in the audience have a background in science of any kind? Nice. I do count psychology, actually. And how many of those are physicists? Okay, so 3 people I really need to work to impress. Good to know. Good to know. So for everybody apart from my 3 fellow colleagues, I'll be giving you a bit of an introduction today about how particle physicists think about the universe. I think some of us have a reputation for being kind of wacky at times, so it's important to give a bit of a translation before we start so you can understand where we're coming from. I'll then talk you through some of the evidence that we think exists for dark matter before talking. Oh, sure thing. Is that a little bit better? Maybe better? Okay, great. No, I'm glad you said it at the start instead of at the end. And then I'll talk about how exactly we go looking for this mysterious particle that we have very little idea about what it is. The search method that I myself work on is called direct detection. So I'll spend the last part of the talk kind of explaining to you what this means and showing you some very pretty pictures from the experiment that I work on, which is called SuperCDMS. Okay, so the purpose of particle physics is to categorize all of the known particles. We turn this into something that's called the standard model of particle physics, which is this horrifying equation just over my left-hand shoulder there. For those of you who aren't physicists, it might look a little bit nicer or more familiar to see it in a bit of a cartoon form. So that giant expression basically just tells us about all of the different particles that exist. So these weird things called quarks and leptons, the particles that cause interactions to occur. So these are what are called gauge bosons. Some of these, like the photon, might be familiar to you. They're the particles that create light, or the Higgs boson, which is also known as the God particle, which is what gives other particles mass. So that giant equation basically explains to you what particles exist, what particles they interact with, how that interaction occurs, the probability of that interaction occurring, and then specific parameters about the particles themselves, their mass, their electric charge, this kind of thing. And our goal is to continue expanding this equation until it can explain all of the physical processes that we know exist. I know there's a lot of educators in the room, so again, I thought I'd give things to you in terms of a report card about how the standard model is doing. The standard model is doing outstanding in 3 out of 4 fundamentals. So it explains electromagnetism really well. It explains the weak force, which is radioactive processes. It explains the strong force, which is how a nucleus stays stuck together. And it explains how almost all of the particles get its mass. However, then it starts to get a little bit shaky. It does a very bad job, or no job at all, about explaining what gravity is and how that interacts with particles. It doesn't explain how one particular particle, the neutrino, gets its mass. It doesn't explain at all dark energy, which is just the label we give to the force that keeps the universe expanding. I don't know about anybody else, but that sounds like a pretty important thing to understand why we haven't just collapsed into a heap. And then finally, it doesn't tell us anything about dark matter. I won't go too much into what that is exactly, because that's what the rest of the hour is for. So when we're looking out at the universe, there's really only 1 or 2 tools that physicists have. The main thing that we do is we basically just look at light with telescopes. Different telescopes can look at different wavelengths of light. You might have heard of ultraviolet or X-ray, but they're all just light, basically. So we can see how bright things are and how big they appear in the sky. If we keep a telescope trained on a single object for a long period of time, we can also know something about its movement, how fast it's moving, what direction it's moving, how it interacts with its neighbors. And these are kind of the two ways that we can figure out how much mass a galaxy has. And weirdly enough, these two methods give us completely different answers. So either we don't trust one of our two fundamental tools about exploring the universe, which is scary, or there must be all of this mass that doesn't interact with light that's throwing off our calculations. Still scary, but a little bit more interesting and heartening than assuming that we don't know what we're doing at all. So I'm going to talk you through a few of these different measurements that we've taken that are coming up with different answers. For most of them, however, I'm going to give you a quick little primer on some quote unquote basic physics. So galactic rotation curves are kind of one of the first pieces of evidence we saw that there might be this dark matter that's out there. When you think about how the galaxy is moving, you can kind of imagine it like this picture on my right, where you have kind of some mass that's symbolized by a sun that's rotating around a black hole at the center of the galaxy. It sounds complicated, but it's basically the same as if I had like a yo-yo on a string and I'm swinging it around my head. The closer the yo-yo is to me, the faster I have to move it to keep it in motion. So based on how fast this galaxy is spinning, we know how much mass must be in there to stop the galaxy from flying apart. So we make measurements of how quickly these galaxies around us are moving, and we see these data points that are given here in yellow and blue. And we then go back to our drawing board and we make all the calculations saying, okay, we've looked at this galaxy with our telescopes. We know how bright it is. We think this is how much mass there is. And we find that the galaxy is moving much, much faster than we think it should be, which is what's given by this dotted line here. Based on the most recent measurements, this tells us that there is about 5 times more mass in these galaxies than we think that there should be. So 5 times more dark matter than there is this luminous stuff that we can see with telescopes. One of the other main pieces of evidence is this thing called gravitational lensing. This one can kind of be a little bit weirder to explain, but the idea is that really heavy objects bend space-time around them. There's one metaphor that I know someone I was chatting to at lunch really doesn't like. But one way that people often use to explain this is if you have a bowling ball that sits on a trampoline, it's going to bend the trampoline around it, which is going to change the paths of things that are moving on the trampoline. So this is the same idea here. If you have this very heavy object in the galaxy, it's going to move the light that's coming from an object that's further away. Instead of this guy traveling out, it goes out and then around to our telescopes. So when we reconstruct what this far object looks like, we trace back our light lines, and we end up seeing something like we see over here, which is we have this one object being duplicated a number of times and kind of smeared out. So this is a cartoon picture, but it actually does a really good job of explaining exactly what we see. So this is a real picture from a telescope, and you can see that there's all these really bright stars in the middle, and you can see some of these galaxies. I hope it's coming up on the screen behind me. Yep. Some of these galaxies you can see are almost repeated or smeared around in kind of a circular shape around the central area here. Similarly, a few over here too. So you can use how many of these guys are appearing and how smeared they look to figure out where the mass must be that's causing them to look like this. And so that's what people at Johns Hopkins have done. They superimposed on the right-hand side here in blue where all of the mass needs to be to make the galaxies look like this. You can see that some of it is overlapping with actual mass that we know about, like these stars, but a lot of it is just what appears to be an empty space. So again, this is telling us that there's all this matter that's causing stuff to move in a weird way that doesn't interact with light. Another really commonly quoted example of dark matter evidence is galactic collisions. So if you think about two galaxies kind of colliding with each other and moving through them, you might kind of think about a sound wave of a bullet moving through water or something like that. You have this thing that looks like a real projectile that's kind of come through, and it's causing this kind of disformation of all of the gas in the galaxy here. This red stuff is the mass that we get when we look at the galaxy with an X-ray telescope. So this is mostly gas, which, contrary to popular belief, makes up most of the mass of these galaxies, not the stars themselves. However, when we then go and measure the mass using other methods like rotational curves or galactic gravitational lensing, we get the answer in blue. And so this tells us a few things. First of all, that the gas in the galaxies moves in a very different way to most of the matter, which is given by this blue guy here. Second of all, this matter is all non-luminous, so it doesn't interact with light. And third of all, it hasn't been deformed at all by the collision. You can see that it's kind of out ahead of all of the pink stuff. And so this means that it doesn't interact with light or other particles or itself. It's basically totally passed through itself completely unharmed. So this means that dark matter interacts very, very rarely. Dark matter also impacts how the universe has evolved. The amount of dark matter that you had at the beginning of the universe basically controls how many stars are in your nearby neighborhood. In terms of some of the other things we've talked about, this is a fairly easy measurement to take. We just look out with a telescope and count all the galaxies that we can see. And then we can compare that with simulations of the beginning of the universe, which is, I'll admit, a little bit harder than just counting things in the sky. And we can see how the structure changes as we inject more and more dark matter into the beginning of the universe. And it turns out that if we didn't have dark matter, things in our universe would look extremely different. We would have no galaxies nearby us. We would kind of be alone in the sky. Whereas we know that we've got a more crowded neighborhood that suggests to us that there is a lot of dark matter that caused the structure to form in this way. The last thing that I'll talk about is the energy density of the universe. Again, this is kind of a map of our nearby universe where the colors are just telling you about the temperature fluctuations in the sky around us. You can do some complicated maths to figure out how to get the energy density of the universe from maps like this. And this basically tells us that about 70% of the universe is made up of dark energy, so this keeps the universe expanding. 25% is made up of this dark matter we think exists, and less than 5% is made up of atoms. So everything all of us study, all of the physics, all of the chemistry, all of the biology makes up less than 5% of the total universe. I really hate that number. It scares me a lot that there's so much we don't know about. And that's kind of why I'm in this field. I find it very unsatisfying that we don't know what all this other stuff is. But I also don't like to bite off more than I can chew, which is why I'm just tackling dark matter for now. And I'll leave dark energy for a second career, maybe. Okay, so now that I've hopefully managed to convince you that dark matter hopefully exists and it's something that's worth studying, how do we go about including it into this giant equation that I showed at the start of my talk? To do this, there's two basic things that we care about. The first is how big a dark matter particle is. What's its mass? And second, how likely is it that we'll have some kind of interaction with another particle? These are the two basic ingredients you need to figure out the maths of dark matter. So the first thing, how big is a dark matter particle? This band at the top of the slide shows all of the different basic dark matter models that exist. You can have ultralight dark matter, light dark matter, WIMPs, which is what I work on, and then something called composite dark matter. But these are all numbers that physicists are used to using. I've tried my very best to translate them into kilograms to show you guys just how ridiculous this search that we're doing is. It's so ridiculous, in fact, that it's really hard to think about this in a way that makes any kind of sense, but here we go, I'll give it a try. So the smallest dark matter candidate that exists is 10 to the negative 57 kilograms. So that's this number down the bottom here. And to save you from counting, that's 0.57 zeros and then a 1. The largest dark matter mass is 10 times the size of the sun, which is 10 to the 31 kilograms. So 1 and then 31 zeros. There's often that kind of fun fact of a googol is 1 followed by 100 zeros. There's pretty close to a googol's difference between these two guys here. Some other things that can kind of help you orient yourself with this are the fact that a speck of dust is around 10 to the negative 9 kilograms. So the difference between the largest possible dark matter mass, so something 10 times the size of the sun, and a speck of dust is about the same scale as the difference between a speck of dust and the smallest possible dark matter candidate. It's absolutely bizarre to wrap your head around. The particular dark matter that I'm looking at is a bit closer to the size of an atom. So it's this 10 to the negative 27 kilograms, which is, much, much more manageable, makes a lot more sense. Again, to kind of give you this sort of sense of scale, The mass of an apple is about zero point 0.1 kilograms, and the mass of the Earth is around 10 to the 24 kilograms. So if an apple was the size of of the Earth, an atom would be the size of an apple. It's kind of the same scale between the two of them. So this is what I use to explain to my partner why physicists tend to be really weird and crazy people sometimes, because we are treating all of these numbers as if they're sensible things to talk about, even though I'm well aware that they're not. Okay, so now that we've figured out just how many different types of particle we're looking for, let's talk about how likely an interaction is to occur. So particle physicists call this a cross-section. And the reason for this is actually the same reason or the same way that everybody else uses the word cross-section, right? So you kind of think about that as how big of an area a thing has. That's its cross-section. And for traditional interactions, this is basically the same thing as a likelihood. If you're thinking about an archer on an archery range and they're trying to hit a target, if they're close to the target, the physical cross-section is going to be very large. So it's really easy to hit the arrow with the target. Sorry, hit the target with the arrow. If the target's further away, it has a much smaller cross-section. You're aiming at a smaller object, and so it's harder to hit. And in that way, a smaller cross-section is associated with a less likely interaction. Of course, things aren't quite that simple, so I'll show you maybe a slightly less traditional example of how physics can start to impact this physical kind of cross-section. So now let's pretend that our archer is shooting at a target that has a magnetic field associated with it. And the cross-section you're looking at is the area which an arrow can go to that will result in the hit of a target. If you're just using a wooden arrow, that's not going to be affected at all by the magnetic field. Feel good? No, that's all right. It's not going to be affected at all by the magnetic field. Your wooden arrow is just going to see the exact same wooden target that it saw before. And the cross-section is, again, the physical size of the target. If you have a metal arrow, however, now the magnet can cause an attraction. So if your arrow is shot a little bit higher than the target, the magnetic field can still pull it down and it will still result in a hit. So you actually have a larger area that you can aim at than just the physical target itself. So in that case, you have a larger cross-section than the target. Of course, there are a lot more complicated physics processes that go into it, but hopefully that gives you a little bit of a flavor for why we call this a cross-section. Okay, so now you know dark matter exists, you know what we care about. How do we measure the things that we care about? There's three main ways that we like to introduce in a cute little way, the make it, break it, and shake it techniques. So if you're making dark matter, the idea is that you have two or more very high energy particles that collide, create this massive soup of stuff, and maybe inside all of that really energetic stuff, you'll be able to spot a dark matter particle coming out. The break it is the opposite process. You hope that out there in space, two dark matter particles might collide with each other and cause some kind of decay, and it will produce regular particles that we know how to detect, and we can go and look for those. Finally, the shake it method, you have a dark matter particle come in, hit some kind of target that you're watching, and cause a recoil within that target that produces an observable signal that tells you something about that dark matter. So making it, or collider production, is when dark matter is produced at particle colliders. So anybody who might have heard of like the Large Hadron Collider, CERN, the God particle, this is the same spot where all of that stuff goes on. So on the left-hand side here, you can see the graphic of just kind of a standard event at one of these particle colliders. What's happened is you've had two particles come in and collide in the center point of the screen here. Each of these yellow tracks is another particle that's being produced by the collision. And these green kind of shapes on either side are the tracks that these particles leave in the relevant detectors. So from two particles, you get all of this. You have to go through all of this and catalog it to figure out if any of it might be dark matter. To give you a sense of scale, this is that collision point in the detector. It's this huge guy, a whole bunch of magnets, electronics, and really complicated detectors inside of a detector. To give you, again, a sense of scale, if you look really closely, you can see that there's actually two people in this picture. Right in the center there, meaning that this whole apparatus is several stories high. I think some people have called it a building-sized Swiss watch in terms of how complicated some of the machinery is. So what actually happens is all of these particles are produced and travel through a whole bunch of different layers within this experiment, where each layer has been specially designed to detect a specific type of particle. So you can see these different particles in different colors with different tracks in this picture here. And so if you see an interaction that occurs only in the outermost layer, you can say, oh, great, if I didn't see anything else, it must be this guy. It's a neutron. If it interacts with absolutely everything, that means it's a proton. If it interacts with the first two, an electron, so on and so forth. So in this way, you can basically do a roll call of all of the different particles that are being produced, figure out what they all are, what their energy is, and then see if when you add all of those together, you're missing anything. Right? Conservation of energy is one of the backbones of physics. And if you get a number that's smaller than the number that you started with, it means that some of this has disappeared, or rather that it's undetectable, or rather that it's dark. So these types of experiments are going on in various parts of the world. As I said, kind of the most famous one is at CERN. There's another really big collider in Japan at Keck and a smaller one at J Park. And in the US, we also have a few smaller linear colliders. So at all of these facilities, they have different types of experiments that are basically sifting through all of the results that are coming out of these colliders to figure out if there might be anything that's dark. The sad news is that nobody's really seen anything yet. So these plots are how we tend to present results from dark matter experiments. It's exactly the same two concepts I was talking about before. Typically, the x-axis is going to be the mass of the particle that you're looking at, and the y-axis will be the cross-section, so how likely that interaction is to occur. Each point on the graph will then correspond to a dark matter particle that has a particular interaction probability and mass. And when you draw a line with an experiment, you're saying every dark matter particle above this line, I should have been able to see. I haven't seen anything, so it means that that dark matter particle doesn't exist. So LDMX, for example, is sensitive to all of this dark matter, didn't see anything, which means that that dark matter doesn't exist. So you can see just from the sheer number of different colored lines on these plots, how many people have gone looking and how many people have turned up nothing. But, you know, we don't give up hope. We just go and try something else. So the breaking of dark matter is often called indirect detection because in this case, you're not looking for the dark matter directly. You're looking at its decay products. So this means that somewhere out in the galaxy, there's dark matter that's producing regular particles, stuff we know how to see, things like light or neutrinos or cosmic rays. This means that there's lots of different signals you can go and look for. So because of that, I tend to think that indirect detection has kind of one of the coolest arrays of different types of experiments. They have big telescopes that are up in space or on the International Space Station, large telescopes that are just on Earth, and a whole bunch of experiments that are either drilled deep into the ice in Antarctica or underneath the Mediterranean Ocean. They're actually designing a new one to go off the coast of Vancouver pretty soon, which is, I'm excited to see how that one goes. So these guys also take place all over the world. They tend to prefer these dark sky sites, which is why you see more in Africa, the Canary Islands, and South America. Special shout out to IceCube in Antarctica, which I think is a very, very neat experiment. And as well as this, as I said, a number of different telescopes that are up in space looking for these types of particles. Even though there's such a vast variety of these types of searches, again, we haven't really seen anything. Same types of plots as before. These guys are all looking and haven't seen anything above this line. These two different plots are just two different observables that detectors are looking for. So on the left-hand side, these are all experiments that were looking for the decay of dark matter to two particles called neutrinos. And the one on the right-hand side was dark matter decaying to different types of photons. Okay, so no making, no breaking. What about shaking? So as I said, shaking is all about the collision between a dark matter particle and a regular particle that we know how to observe. Because of this, these guys tend to be the kind of the smaller on terms of experimental scale. So on the right-hand side here, you can see one of the new up-and-coming experiments, LZ. They just published some results in the last few months, which are very, very exciting. And this main part of the detector, which is shown in a cartoon form here, is only a little bit taller than your average person. So what happens here is you have your dark matter particle coming in, some form of reaction which produces something that we know how to interact with, which is then observed and mapped back to a type of dark matter particle. The three ways that we can look for dark matter in this way are using signals that are made out of light, made out of charge, or made out of heat. And this tends to dictate how big your actual detector can end up getting, with the light scale experiments tending to be the largest and the heat ones being the smallest. So if you're seeing with light, you basically have this really bright burst of light when your dark matter particle comes in. These photons are then allowed to bounce around the detector until they're picked up at your sensors here, which are often called photomultiplier tubes or silicon photomultipliers. The gotcha with this is that it's not light in the way that we're used to thinking about light. Normally, you'll only get maybe 10 photons, so 10 small particles of light that you have to try and track throughout your target and hope get picked up at one of these sensors here. So you have to make sure that these guys are extremely, extremely sensitive. I actually have a colleague who I did my PhD with. We worked on one of these light detectors, and he specialized in these sensors. He's since left academia and he's working for a camera company because in some ways these are just extremely fancy cameras. And he was like, it's so boring. They're just seeing everything. The other way that you can go looking for this is looking for charge. So in this case, your dark matter comes in and it's going to knock an electron out of its spot in the nucleus. This then produces a hole, which is basically treated as a positive particle that's the same size as an electron because you have the electron jumping and then the hole moving in the opposite direction. Normally, in a regular environment, the electron would just relax back into its natural state. But if we apply a potential difference or an electric field across the crystal that we're looking at, it will force the electron in the hole to move in opposite directions. So you end up tracking all of this charge throughout your crystal, and you can record it at either side and figure out how much energy must have been produced in this collision in order to have excited this many electrons. Looking for things with heat is basically a variation on looking for them with charge. Again, you have an interaction that's going to produce your electron, but now instead of applying a small potential difference, you employ a really large potential difference. So instead of meandering across, the electrons and holes, they speed straight up to the sensors. But because they're moving really quickly through the crystal lattice now, they're causing all of this vibration, which mathematically is basically the same thing as heat. And we can observe these vibrations using quantum sensors. So we've got these superconducting sensors that are really, really cold, and they pick up these very small changes in heat that occur when these guys are moving quickly. So you can kind of get both a charge signal and a heat signal, which is very useful if you're trying to understand specific things about the dark matter. Just like the other two, there are a lot of different sites. However, I will say that each of these experimental sites can host anywhere from 1 to like 20 different experiments. So this is not at all
That's,
a
that's good.
full survey of all the different experiments that exist. But again, you can see that there are a lot of places. Snow Lab, which is where I spend probably about a quarter of my time since I moved over here, is the biggest and the deepest. But there's a lot of other research facilities in Europe, China, Asia, and more
That's
recently, Australia. One of my favorite things about doing my PhD over there was this was when the lab was getting built. So I got to see the lab here go from kind of just a hole in the ground to a proper, fully fledged experimental laboratory. Despite all of this exciting work, we're still in kind of a sorry state of affairs. We go really deep underground because I would think I was talking to somebody at lunch about muons or cosmic rays, but these guys are basically showering the surface of the Earth at really, really high rates. Basically, if you put your hand out like this, there's going to be one muon going through your palm every second. Maybe that doesn't sound like a lot to you, but it's a huge amount for a dark matter experiment. They basically swamp out any sort of dark matter signal that could be occurring on the surface of the Earth. So because of this, we have to go deep underground in all of these labs in order to shield our experiments using rock. The way we quantify this, because different types of rock do different jobs at shielding, we talk about this vertical overburden in terms of kilometers of water equivalent. So if you replaced all of that rock with water, how deep would that water be? And you can see that SNOLAB is basically winning the race here with 6 kilometers of water equivalent. Technically, Jinping Lab in China is deeper, but they're inside a mountain, so I don't think it counts as much. It's more fun when you're going deep underground. But the thing that's really important is that this is the background reduction that you get when you go this far underground. So SNOLAB gets a reduction of about a factor of 1 billion. So we go from 1 muon passing through my hand every second to 1 muon passing through my hand every billion seconds. That's pretty good odds for only having to go a little bit underground, I would say. But yes, despite all of this hard work, we still haven't really seen anything. As I said, LZ, one of the most recent experiments to come online, has kind of just put results out really recently that have pushed out a lot of this possible dark matter space down here. However, if you're an optimist like me, you might say, hang on, whole bunch of white stuff over here. That means there's all these types of dark matter particles that nobody's even tried to look for yet. Why not? So the reason for this is these dark matter particles are a lot lighter than the dark matter particles over here. They're about 100 times lighter. This means that when they interact with an atom, the amount of energy that you get is very, very small. Think about it as if all of these experiments are playing pool with a regular cue ball. You know, you're lining up the shot, hitting that white ball into all of the other colored ones, and things go flying. It's really easy to see what's going on. When we start moving into this region, instead of playing with a pool ball, you're playing with instead of playing with a cue ball, you're playing with a ping pong ball. No matter how hard you hit that ping pong ball at the pool cues, they're not going to move very much at all. So it's really, really hard to see. And you need a specially designed experiment to be able to observe these low energy events. And this is exactly what my baby, Super CDMS, is doing. So Super CDMS uses 2 different atomic targets that we hope dark matter will interact with. We use silicon crystals and we use germanium crystals. We also use 2 different types of sensor technologies. We have sensors that are specially designed to detect charge, and those that are designed to detect heat. So these are the really special ones that I've spent a lot of time working on over the last year. In total, we have 24 different individual crystals that are arranged into 4 towers and cooled to 13 millikelvin. Again, Kelvin might be something that you guys aren't used to working in. Perfectly fine. Room temperature is about 290 Kelvin. Outer space is about 2 Kelvin, which means that our fridge is about 100 times colder than outer space, making it potentially, it's definitely one of the coldest places on Earth, but potentially one of the coldest places in the universe, which I think is pretty cool. To give you a sense of scale, these detectors themselves, because they're built in Canada, are about the size of a hockey puck. So that's how big these guys are, kind of yay big. These then get arranged into different towers depending on exactly what technology we're using to detect the signals, where they're all enclosed inside their little special copper housings, and then we have all this fancy readout that has to work at these absolutely freezing cold temperatures up in Sudbury. Very cold. Our fridge itself is made out of what I like to call a kind of copper babushka doll. Because it's really hard to cool things to this kind of temperature, we do it in stages. So each of these cans is held at a different temperature. The biggest one is about 1.5 meters by 1.5 meters, and that's held at room temperature. The next can down, a little bit smaller, is held at 50 Kelvin, which is about the temperature that you start to get liquid nitrogen for anybody who's dealt with that in their labs or been to a science fair where they make liquid nitrogen ice cream. The next can down is about 5 Kelvin, which is when you start to get liquid helium. And then below that, we have to invoke some really special physics processes involving helium to get below 1 Kelvin, below 230 Kelvin, 230 millikelvin, and then finally down to 13 millikelvin at the final stage where the detectors are. Because it's really difficult to get electronics to operate at these really cold temperatures, you might be able to see that our detectors themselves are in this section just here. So they end up ending. They're the only things that are held within the smallest, most cold can. The towers themselves are actually twice that size, just so we can get all of our electronics just that little bit warmer to make sure that things are working as they should be. This beautiful copper babushka is then placed within a whole bunch of shielding. Even though we're underground, there are still other concerns about being in this environment that mean we want to protect this guy with a shielding apparatus that ends up being about 4.5 by 4.5 meters. This is all then placed on a specialized seismic platform. This guy is underground at Snow Lab, which is actually in an active mine. I don't know how many of you guys have experienced mining, but they often use a lot of explosives. And you can imagine that if you had this big can of all of this copper just hanging, and then all of a sudden the floor starts to shake, it causes real issues with the way our detector operates. So we have this all seismically isolated on the specialty platform here that keeps it all nice and still when our miner colleagues are blowing things up outside. So Snow Lab itself is about 2 kilometers underground, 400 or 500 meters north of here. And again, to give you a sense of scale, it's about 3.5 CN towers below the surface of the Earth. You take an elevator down there. It only takes a few minutes because the elevator, or the cage as we call it, travels at about 30 to 40 kilometers an hour. It's pretty quick. You get down, you have to walk another 2 kilometers in order just to get to the lab. Then you have to clean off all of your equipment, take a shower, mask up, put all of your protective equipment on so that this place stays one of the cleanest places in the world inside one of the dirtiest possible mining environments. It's a lot of effort that goes into keeping this place clean, and I'll show you just a little bit of some of what we do for that. So I talked a little bit about why muons are a problem, and hopefully this kind of helps you figure out why that might be. So for the dark matter particles that we're looking for, we expect to see less than 5 hits every year in a detector. And that's kind of the maximum amount. If we're seeing 5 hits, we're probably going, oh my God, something's wrong. We're doing too good a job at this. So because of that, in order to have the best possible performance of our detector, we need to try and reduce, or worst case scenario, really properly model any interactions that are coming from stuff that's not dark matter. So this is going to be basically radioactive particles in the environment. However, it's not radioactivity in the way that you might be worried about it in your everyday life. Bananas are too radioactive for us. Humans are too radioactive for us. This is very, very trace elements that we're talking about here. And in general, there's 3 ways this can get into our experiment: through the contamination of materials, through the activation of materials, and from just the general lab environment itself. So, like I said, all materials have these really low levels of uranium, thorium, and potassium. To get around this, we spend a lot of time, and I'm talking years, measuring all of the different possible vendors we can use to get materials. So this is just a small subset of all the different types of copper that we measured to try and find the lowest radioactivity copper that we can get. It then gets machined, and because machine shops are dirty places, it arrives at our lab looking something like this, which, even though it's very radioactively clean copper, is not particularly clean in and of itself. So we go through a really specialized cleaning process to turn this guy into this over the process of 1 day. In the case of copper, this involved an acid bath. I've got some cool videos of that I can show you as well. But basically everything that we use, not just the copper, has to go through this kind of hardcore selection and cleaning process. Even after all of that, the material contamination is going to end up making up about 40% of our total background in our experiment. Another 40% comes from the material activation. So this is due to our pesky muons again. When things are at sea level, they're exposed to cosmic rays, so all of these high energy particles that are coming down from space. This can basically excite all of the different atoms that you have in copper, germanium, and silicon and cause them to produce other types of radioactive isotopes, which is a bit of a problem for us. Basically, to try and account for this, we avoid flying anything. All of our stuff that gets produced gets driven here by truck or sent over from Europe by ship. And when we do this, we very carefully track the exposure. We literally put in air tags with everything that we ship and track the latitude and the longitude and the altitude, in some cases, of where these guys are going so that we can figure out exactly how many cosmic rays they've been exposed to. For extremely sensitive pieces, like our detectors here, we go even more extreme. We use this crazy shielding where, so these guys are all wrapped up and carefully placed inside foam to protect them. This foam is then placed inside this big lead canister, which is then placed inside of an even bigger stainless steel and lead canister that weighs, I think, about 12 tons, which is then placed inside a shipping container and shipped from Europe to What's said Australia, from Europe to America, where we could then start to continue the fabrication of these detectors here. So after all of that tracking, we use that to calculate how many days we've basically had these guys sitting out at sea level for. When we first started designing the experiment, the goal was that they would be exposed for less than 60 days. We actually got less than 40, which was very, very exciting. We only had two towers that kind of crept up to this upper limit, but this was unfortunately because they were fabricated during COVID. So when things started to get shut down, they were left on the surface for a little bit longer than we intended. But even given that, we're really well on track in terms of our activation backgrounds here. The final 20% of our backgrounds are coming from these environmental sources that I mentioned. So things like dust in the lab, the rock in the lab walls, and human activity, which are again going to carry all of these really trace amounts of radioactivity. Another unique problem of being underground that people with basements might know about is that the further underground you go, the more radon that you have. Radon can decay into radioactive lead. Again, don't worry about it in your basement. It's not dangerous to you, but it's dangerous to our experiment. We can't really prevent any of these from cropping up. They're just things that exist underground. So instead, we protect and we shield our equipment as best as we can. So you can see me here on the right-hand side handling one of our detectors. I don't think I've got any skin exposed, actually. My head's a little bit small, so the hood fits right over me. But basically, you want to reduce any kind of exposure of your skin or your hair when you're handling these detectors. We've also built up this lead castle and pulley shielding and magnetic shielding around our detector as well to protect it whilst it's operating. Okay, so now for some pictures of the current install process. So this has all been going on over the last year or so up at Snow Lab. I've spent probably almost a week a month up there since I moved over to Canada in 2023, which has been quite the education for a girl who grew up on the beaches in Australia. But as of now, all four of our detector towers are underground. They've been tested that all of their electrical connections survived, and we're in the process of doing trial runs to install these into the cans. Last year, or sorry, no, end of 2023, we actually had the chance to test our detectors for the first time in an underground fridge. So our lovely neighbors down in Snow Lab, Cute, have a fridge that's very similar to our own, and they loaned it to us for a couple of months so that we could test our detector. So this is actually how it gets installed. This is the detector itself. It then gets flipped upside down and inserted into the fridge here. So you can see this is the top of the detector in this picture here. This all then gets pushed up and placed inside this aluminum shielding just here, which then gets lowered inside of even more lead shielding and cooled down so that we can take data with it. Our fridge looks a little bit different. It's nice and made of gold instead of copper. And it's been underground for a few years as well. One of the scientists who installed it was actually hired during COVID and had very little experience working with one of these fridges. So he said he spent a very stressful few months with people shouting at him over Zoom not to break anything while he tried to put it together. It seems like he's done a pretty good job. We've done a number of cool down tests and are in the middle of another one. But this guy is also underground and operating very well, ready for us to start hooking things up to it. This is some of that cleaning I was talking about. The copper cans have definitely been the things that have taken the most amount of time and effort to clean, but we've started installing them underground. So this is the biggest one that I was talking about, that outer can that's held at room temperature. And these are some of the smaller ones where we're kind of trialing out how we're going to be lifting them during cleaning and what they look like when they're ready to be shipped underground. This is another picture of those cans where this is the inner four. So you can see again, maybe it's helpful to have a person for scale. Here's me at the background glaring at everybody to make sure they're keeping all of their background protection stuff on. But this is what they all look like when they're suspended from each other. You can maybe make out these small black ropes. Yes, you can still see them on the projector. That's all that's keeping all of these cans hanging from each other. You might be able to see these little white spacer bars. Those are basically bumper bars for whilst we're moving this thing around in the lab, and they'll be removed once we cool things down. Our shield wall is also increasingly being constructed. So this is the big tube that ends up connecting all of these cans to the fridge's cooling power itself. And you can see that we're going through a lot of effort to make sure that we're getting as much lead packed around this guy as we possibly can, because lead is one of the best shielding components that are out there. Okay, So all of this effort to put this thing underground, where do we think it's going to get us? Well, we're pretty excited. Remember that big old white gap in the experimental landscape I was talking about? We're now basically closing that whole thing off. With our four different types of experiments, we're able to kind of probe slightly different types of dark matter. This was the thing that really drew me to Super CDMS in the first place. I think it's a very versatile and well-rounded experiment because even though you've only got the one fridge with a few different types of detector towers in there, you're effectively running four different experiments at any given time, which I think is really, really cool. So if dark matter lives inside of any of this white space, we should be able to see it once we start taking data within a few years. So, in summary, hopefully now you understand why dark matter is such an active field of research. It makes up more than 80% of the matter, but we don't really have any idea what it is. There's this huge range of possible masses that we think that it could be, and we're basically taking bite-sized chunks out of this parameter space as we go. There's lots of different possible ways that you can go about trying to detect it. And one of them is super CDMS, the coldest place on Earth / the universe in one of the least radioactive environments in the world. We're doing a lot of very hard work to explore new types of sensor technologies and dark matter parameter space that hasn't been investigated yet. And we're hoping that once we switch on, we'll be a leader for the dark matter field in the coming years. Thank you.